Section 4.3, determining function behavior from the first derivative. So I want you to think back to section 4.1 when we were talking about absolute extrema and extrema on an interval. So when is the function, how can you tell whether the function is increasing or if the function is decreasing without actually looking at the graph? I hope you remembered that you can tell that the graph is increasing. F of x will be increasing if f prime of x is greater than 0. So the first derivative is the slope. If the slope is positive, the function is going to be increasing. Similarly, if f of x is decreasing if the first derivative is less than 0, so the slope would be negative. So how can that help us find and graph our function? We're going to use the first derivative test for the relative, sometimes called the local extrema. The first thing you need to do is identify all the critical points. Remember, the critical points is where the first derivative is either equal to 0 or is undefined. Secondly, you're going to make a labeled sign chart by testing values between the critical points to determine if the first derivative is positive or negative. And then you can determine whether the critical value is a relative max. If f prime changes from increasing to decreasing, that's going to be a peak. Or if it's a relative min, so f prime changes from decreasing to increasing, it will be a valley. Let's do a couple problems and make sure we got this. Number 1, on which interval or intervals is g of x increasing? Can you justify your answer? So we need to find our first derivative, so go ahead and pause that and find your critical values from your first derivative. I get that my first derivative is 300 minus 3x squared. Now I need to set that equal to 0 to find my critical values. I get that my critical values are negative 10 and 10, so now I need to make my labeled sign chart, and this is what I mean by a labeled sign chart. Basically, you're going to have your number line using negative 10 and positive 10. Now if I plug a number in less than negative 10 into my function, then I'm going to get that it's going to give me a negative value. If I plug in a number between negative 10 and positive 10 into my first derivative, I find that I'm going to get a positive value. And if I plug a number in greater than 10, I'm going to again get a negative value. So I can see that my function decreases, and then it increases, and then it decreases. So I know that my function is increasing between negative 10 and positive 10. Now we're going to do a similar problem. Number 2 wants to know on the domain of 0 to 2 pi, when is that function decreasing? Again, find the first derivative. A note of caution, you're going to have to use the product rule. There I have my first derivative, and I'm going to set this equal to 0, and I'm going to factor out in e to the x, kind of rearrange these. I'm going to factor out that e to the x because remember that e to the x is just a constant. We're having a constant raised to a power. It's always going to give us a constant. When I set this equal to 0, cosine of x minus the sine of x equals 0 is the same thing as saying when is the cosine of x equal to the sine of x. And if we think about the unit circle, we know that that happens at pi over 4 and at 5 pi over 4. In the first quadrant they're both positive, and the third quadrant they're both negative. So those are my two critical values, and now I need to make my lined sign chart and determine where is the function increasing or decreasing. Again, pause the video and try to do that. When we do our sign chart, we can see that the function h of x decreases between pi over 4 and 5 pi over 4. Number 3, let f of x be twice differentiable function with f prime of x equal to the sine of x minus 1. Find all critical points of f of x on the open interval 0 to 2 and classify each as a relative minimum, maximum, or neither. Let's make sure you're paying attention to the details. They're actually giving you the derivative function, so we don't have to take the derivative. We simply have to find when that is equal to 0, and then determine whether they're maxes, mins, or neither. So let's first of all think about when the sine of theta is equal to 0. And so in that case, theta would be 0, pi, 2 pi, etc. So that means that x minus 1 is going to equal 0, pi, 2 pi, and so forth. When we solve this for x, we're going to get that x equals, when I add 1, 0 to 1 is 1, pi plus 1, 2 pi plus 1. And if we think about this, pi is 3.14, so that value and that value are not in my interval. The only critical value I have in that interval is 1. So my sign chart, including the endpoints of the interval, is going to be 0, 1, and 2. And then testing values, if I plug in a number between 0 and 1, I'm going to get a negative value. If I plug a number in between 1 and 2, I'm going to get a positive value. So this function decreases and then increases. Therefore, we can tell simply by looking at those slopes that I just drew in that 1 is a minimum, because the function decreases and then increases. Problem number 4, find the relative maximums and minimums of that given function. This problem really is fairly straightforward. I just want you to go ahead and pause the video and do the steps that you have written up above in the important ideas box for number 2, the first derivative test. I have my first derivative. I need to set this equal to 0. To make the factoring easier, I'm going to factor out a 3. And then I can see that this is going to factor as x plus 3 and x minus 1. So my critical values are going to be x equals negative 3 and x equals positive 1. My next step then, number 2, is to make my labeled sign chart. Negative 3, positive 1. If I plug in a number that's less than negative 3 into my first derivative, the factored form is probably going to be the easiest. I get that it's positive, so it's increasing. Plug in a number between negative 3 and 1, so if I plug in 0, I'm going to get a negative number, so in that interval it's going to be decreasing. And then if I plug in a number that's greater than 1, it's going to be positive, so that's going to be increasing. So I can see I'm going to have a max at negative 3, and I'm going to have a min at positive 1. I actually should write those as x equals negative 3 and x equals 1. So that's where my maximum and minimum occur. So I can say that I'm going to have a relative max. If I plug that negative 3 into my original equation, then I'm going to get 32. So I have a maximum of 32 at negative 3. And I have a relative min. Again, if I plug that 1 into my original function, I can see that I get 0 out. So I have a relative minimum of 0 at 1. And last problem, the derivative of g of x is shown in the graph below. For which values of x does the original function have a maximum or a minimum? I think the easiest way to explain this, especially on a video, is to convert this graph into a line chart. So I can see that it's crossing the x-axis at negative 3, at negative 1, it touches the x-axis at positive 2, and again at positive 4. Remember, when the first derivative is equal to 0 is going to be when there's a critical value of the function. So now if I'm not even plugging anything in, I can see that on the left side of negative 3, the function is below the x-axis, so it's negative. Between negative 3 and 1, it's above the x-axis, so it's positive. Between negative 1 and 2, the first derivative is below the x-axis, so it's negative. Between 2 and 4, it remains negative. And then after 4, it's positive. So again, if I draw on my lines, my function is kind of following that behavior. And so I can see here it's going to reach a minimum at negative 3. And again, it's going to reach a minimum at x equals 4. And I can see here that the graph went up and then down. So it's going to have a maximum, relative max, at x equals 1. If you have any questions on how to use the first derivative test to determine the behavior of the original function, please make sure you come to class, and I will be glad to answer all your questions.